Hi everybody. Well, we now need to begin with this very important theorem in probability, which is known as the Bayes theorem. So what do I mean by the Bayes theorem? Before I lay down the formal statement which is said by this theorem, let me tell you what is that problem which this theorem is used to resolve. For example, you have two jars with you, okay? Try to understand the problem very nicely. Here you have 3 red balls and 4 black balls, fine. Here you have 5 red balls and 6 black balls. Say this is jar 1 and say this is jar 2. Try to understand the problem now. I am selecting a jar at random and I am drawing a ball from it. There are 3 red balls and 4 black balls in jar 1, 5 red balls and 6 black balls in jar 2. Now, if I tell you that I am actually from jar 1 drawing a ball, listen to the information that is being given to you. I am saying I am already out of the 2 jars specifying that the ball is being drawn from jar 1. Then what is the probability that the ball drawn, the single ball drawn from jar 1 is a red ball? So, first of all, let me say I am defining 3 events. A single ball is drawn, fine. I am saying ball is drawn from jar 1. E2, this is say E2, ball is drawn from jar 2. E1 is the event of drawing a ball from jar 1, E2 is the event of drawing the ball from jar 2, and A is the event that the ball drawn is red. Now, the first scenario that I just dictated to you was that out of the 2 jars, if I am already specifying that from which jar the ball is being drawn, the situation becomes very simple, right? If I am saying that the ball is being drawn from jar 1, then tell me the probability that the drawn ball is a red ball. That means probability I have to tell that the ball drawn is a red ball when I already know that the ball is being drawn from jar 1. What is the probability that the ball drawn is a red ball if it is already given to you that the ball is being drawn from jar 1? That means what is the probability of occurrence of event A when event E1 has already occurred? Isn't it? We have done condition probability nicely. What is the probability that the ball drawn is a red ball when I already know that it is being drawn from jar 1? E1 is the event that the ball is being drawn from jar 1, A is the event that the ball drawn is a red ball. So, probability of A by E1 is something that is nothing but the probability of drawing a red ball from jar 1. This is very simple. What is the probability of drawing a red ball from jar 1? You know that there are 3 red balls in total, there are 7 balls. So, 3 by 7 is the probability of a red ball being drawn from jar 1. Similarly, if I say what is the probability of drawing a red ball from jar 2, you will say 5 by 11 is the probability of drawing a red ball from jar 2. That means I am already giving to you that from jar 2 the ball is being drawn. Then what is the probability that the drawn ball is a red ball? So that would be nothing but probability of A by E2. And that would be 5 by 11 because there are 5 favorable outcomes and 11 total outcomes from jar 2. From jar 2, when you are drawing a ball, that is a random experiment. What are the possible outcomes? 5 red balls, 6 black balls. So there are 11 possible outcomes, all equally likely. 1 by 11 is each one of them probability. 1 by 11 is the probability of each of the possible 11 outcomes from jar 2. What is the probability that the drawn ball is a red ball? Number of favorable outcomes are 5. Total number of outcomes are 11, so 5 by 11 is this probability. And the very probability of drawing a red ball from jar 2, if these 3 are the respective events, is written as probability of A by E2. That means still here the situation is very simple. if I am specifying to you from which container is the ball is being drawn, then it's very simple for you to answer the probability that the drawn ball is of a particular color, whether red or black. Let's move to a reverse condition. Second scenario. I am saying there are 2 jars. In the first jar there are 3 red balls and 4 black balls. In the second jar there are 5 red balls and 6 black balls. One jar is being selected at random and a ball is being drawn from that jar. If I am now giving you that I know the color of the ball being drawn for sure, then what is the probability that it is being drawn from a particular jar? Exact reverse. In the previous case, I knew from which jar the ball was being drawn, and then I was calculating the probability of the drawn ball being of a particular color from that jar. Now I am saying the reverse of it. I am saying if I know that the ball drawn is a red ball, then what is the probability that it is being drawn from jar 1? If I am already aware that the ball drawn is a red ball, then what is the probability that it is being drawn from jar 2? So if I am already aware that the ball drawn is a red ball, that means already event A has occurred. What is the probability that the drawn ball is from jar 1? What is the probability that E1 event will occur? So what is the probability that E1 will occur when A has already occurred? It is exact reverse of this. Here it was, when you already know that the ball is being drawn from jar 1, what is the probability that it is a red ball? Here I am saying, if you already know that the single ball drawn is a red ball, what is the probability that it is being drawn from jar 1? What is the probability that the ball drawn is from jar 2 if you already know that it is a red ball? These are questions which are answered by Bayes' theorem. Basically, it is the reverse probability. It is the issue of reverse probability which is answered very nicely by the Bayes' theorem. So you understood the condition probability sense, and now I am talking about the reverse of it. You will be aware about the color of the particular ball being drawn, but you will be needing or interested in evaluating that that ball is being drawn from which jar. What is the probability of that ball being drawn from jar 1 or being drawn from jar 2? Exact reverse of this. This is exact reverse of this. Cool? So let's see what actually Bayes' theorem says. We've got the concept which is actually the basis, the foundation of the Bayes' theorem. Let's try to now formally understand the meaning of Bayes' theorem. It says that let S be the sample space, let S be the sample space, and E1, E2 and so on till En be n mutually exclusive and mutually exhaustive. So I hope you remember the meaning of both these terminologies. When do you say that a set of events is mutually exclusive? When do you say that a set of events is mutually exhaustive? And when do you say that a set of events is mutually exclusive as well as mutually exhaustive? Now this set of events is mutually exclusive and mutually exhaustive. Events associated to a random experiment okay. So these are n mutually exclusive and mutually exhaustive events, and S is the sample space. All these are associated to a random experiment. Let A be an event, let A be an event which can occur, let A be an event which can occur with E1, or it can occur with E2, or it can occur with E3, or it can occur with En. I am saying let A be an event which can occur with either E1 or E2 or E3 and so on, or En. Then A is an event which can occur with E1 or E2 or E3 or En. Then what is the probability that if Basically, if event A has already occurred, what is the probability that it has occurred with E1? Are you understanding? A is one particular event which can occur with E1 or E2 or E3 and so on, or En. These are the sources of occurrence of an event. This event can occur from this source or this source or this source or this source. If I know that event A is definitely occurring, what is the probability that it is being occurring with source E1? What is the probability that it is being occurring with source E2? What is the probability that is being occurring with source E3 and so on? What is the probability that event A is occurring with source E1? What is the probability that the ball drawn, that is red, is being drawn from the first jar? That is being generalized in here. So I can say EI. Probability of occurrence of event A with the source EI. In the place of I can have E1, E2, E3 and so on till En. Okay? Chances of occurrence of event A with source E1, chances of occurrence of event A with source E2, chances of occurrence of event A from source E3, chances of occurrence of event A from source E4 and so on, chances of occurrence chances of occurrence of event A from source En. What is this? This, according to the Bayes theorem, is given by probability of the source multiplied by probability of occurrence of that event from that source. This is very simple, right? This is something that is reverse of it. This is simple conditional probability. What is the probability that the ball drawn is red from jar 1? So this was simple. Whole upon probability of E1 into probability of A by E1. That means probability that the first source is selected multiplied by probability of occurrence of event A from the first source plus probability of the selection of second source multiplied by probability of occurrence of event A from the second source plus probability of occurrence of the third source multiplied by probability of occurrence of event A from the third source plus and so on probability of the nth source being selected multiplied by probability of occurrence of event A from the nth source. Are you understanding? Because A event can occur from any of the sources. It can occur with any of these E1, E2, E3 up till En events. So, probability of selection of the first source multiplied by probability of occurrence of event A from the first source plus probability of selection of the second source multiplied by probability of occurrence of event A from the second source and so on, probability of occurrence of the nth source multiplied by probability of occurrence of A from the nth source. And in the numerator sits that particular expression which is concentrating according to this I. If this I is 2, then probability of E2 into probability of A by E2 and beneath this entire sum. If I is 3, then probability of E3 into probability of A by E3 and beneath it this entire sum. So I can say this is true for every I varying from 1 to n. Therefore, probability that event A has occurred from the ith source is probability of selection of the ith source into probability of occurrence of event A from the ith source divided by summation of probability of the ith source into probability of occurrence of event A from the ith source. Let me write this is J, because I is standing for the specific I which is here. J is varying from 1 to n, and this is true for all I varying from 1 to n. Is it clear? How do you get this? How do you get this? Let's try to prove this. I am having a sample space. So that's my sample space. E1, E2, E3 up till En are mutually exclusive and mutually exhaustive events. That means they are pairwise disjoint. You know that EI intersection EJ is phi for all I not equal to j and I and j varying from 1 to n. That means there is absolutely nothing common between any two, right? They are all disjoint events or subsets of the sample space. Moreover, because they are mutually exhaustive, E1 union E2 union E3 and so on union En is my complete sample space. That means I can write sample space as the union of these disjoint, pairwise disjoint sets. So I will be having a situation like this. What will be the situation? Say this is set E1, E2, this is E3, E4 and so on, this is En. You can see when you take the union, you are getting the sample space and also they are completely disjoint from one another. There is nothing common between any of the two subsets of S among any EIs. So here this would be the situation because EIs are nothing but mutually exclusive and mutually exhaustive events. Now if S is this union, I know that A is any event associated with a random experiment. So A will be a subset of the sample space. Suppose this is my subset of the sample space. Let me just take it in a very general fashion. So this is my set A. What is this portion? Tell me. What is this shaded portion? This is the intersection of event A with the event E1. This portion is A intersection E1. After that, tell me what is this portion? This is intersection of event A with event E2. So it is A intersection E2. After this you have this portion. Clearly this is what? This is A intersection E3. And so on. If I talk about this portion, what is this? This is A intersection E4. And similarly if I talk about this portion, this is nothing but intersection of A with event En. So it is A intersection En. Okay, why am I doing this is A can be written as A intersection S, isn't it? Between A and S, what is the common portion? Of course A. So A intersection S is nothing but A. A is a subset of S. But S is nothing but E1 union E2 union E3 and so on union En. By the distributive law, you know that this can be written as A intersection E1 union A intersection E2 union A intersection E3 and so on union A intersection En. This is A. If that's A, that means in short, how can I write A then? How can I write A in short? In the form of summation, I can write A as summation of A intersection EI, I varying from 1 to n. It's A intersection E1 union A intersection E2 union A intersection E3. So not summation, but I can write this as complete union of A intersection EI, I varying from 1 to n. Like this you can write. Not summation, but a big union. Now what happens is if that's my A, what is my A? Let's rewrite A. A is A intersection E1 union A intersection E2 union A intersection E3 and so on union A intersection En. Then probability of A is probability of this union. Now you know that probability of A union B is probability of A plus probability of B when you know that they are mutually exclusive events. Here these are finitely many events given to you. You can clearly see that if I talk about A intersection E1, A intersection E2, A intersection E3, A intersection E4 and up till A intersection En, all these are subsets of the sample space which have absolutely nothing in common. They are mutually exclusive events for sure, you can clearly see. Just like E1, E2, E3 up till En are mutually exclusive. Similarly, A intersection E1, A intersection E2, A intersection E3 and so on, A intersection En are, you can see they are mutually exclusive. They have nothing in common. right? So the moment I am sure that these are mutually exclusive events, A intersection E1, A intersection E2 and so on, A intersection En, then probability of this union is just the sum of their individual probabilities. So it will be probability of A intersection E1 plus probability of A intersection E2 plus and so on probability of A intersection En. Is it clear? I can write this in short as summation probability of A intersection EI, I varying from 1 to n. This is probability of A. If I talk about probability of A intersection EI, by multiplication theorem on probability, I can write this as what? Can't I write this as probability of A into probability of EI by A? Can't I write this as probability of A into probability of EI by A? Or I can also write it as probability of EI into probability of A by EI. Let me name this as one rather. You know this probability of A intersection B is probability of A into probability of B by A or probability of B into probability of A by B. So I have written it like this: by the multiplication theorem on probability, this is my final probability of A expression. Now, if I talk about again probability of A intersection EI, I can also write this as probability of A into probability of EI by A. It is probability of EI by A that I am finding the expression for. Probability of EI by A I wish to find. So I'll keep it as it is and take the rest of the things to one side. Understood? But probability of A intersection EI is what? What is probability of A intersection EI? It is probability of EI into probability of A by EI. By multiplication theorem on probability, probability of A intersection EI is probability of A into probability of EI by A or probability of EI into probability of A by EI. Now, denominator is probability of A. Probability of A is given to me this by equation 1. It is summation of probability of EI into probability of A by EI, where I is varying from 1 to n. Or let me write J over here. Right? Let me write J over here. I'm just changing this variable. Understood? And this I was chosen randomly, so this is true for all I varying from 1 to n. Clearly you can see this and this are matching completely, and therefore this is the proof of my Bayes theorem. Hence, proved. You understood? This is the very proof of the Bayes theorem. Now that we've got the Bayes theorem, it's time to actually apply the Bayes theorem. The problem was very clear to you that in what context is Bayes theorem applied. So again, if I am saying that I have suppose 3 containers, okay, here I have 4 red, 6 black balls, here I have 4 black, 6 red balls, here I have 5 black, 5 red balls. Say this is jar 1, jar 2, jar 3. I am saying one jar is selected at random and from it one ball is drawn. If the drawn ball is red, find the probability that it's drawn from jar 1. Now, if the statement of Bayes' theorem is understood by you and the formula is learned by you very nicely, you can clearly get the solution of this. This is a homework for you. I'll be discussing the solution of this in the next session, so I'll see you then. Thank you.